All right, everyone. I am very excited to be moving on to chapter 6, which deals with power series. So basically, what it's going to do is it's going to take what we have previously done, with all those like the ratio test, the root test, things like that, and it is going to apply it to more calculus-y stuff. So like derivatives and that kind of thing. And it's very cool. It's very, very, very neat. And we are going to end chapter 6 with a very cool proof that at the beginning of this class you would have thought was very hard, but then now you'll see it's really not that bad. And so this is a very cool uh, chapter for us to be in. So obviously we're starting with section 6.1. For those of y'all in my class at CCC, you have the handout for section 6.1. 6.1 is power series and functions. Let's first define what a power series is. A series of the form, the sum of Cn xn, which would then be equal to, if I plugged in 0 first, C0. Then if I plugged in a 1, C1x. Then if I plugged in a 2, C2x squared. Then if I plugged in a 3, C3x to the third. If I plugged in a 4, C4x to the fourth. On and on and on. Is a power series centered at x equal to 0. And then a series of the form, the sum of Cn x minus a to the n. Again, plug in a 0, you get C0. Plug in a 1, you get C1 times x minus a. Plug in a 2, you get C2 x minus a squared. Plug in a 3, you get C3 x minus a to the third. Plug in a 4, C4 x minus a to the fourth. On and on and on. Is a power series centered at x is equal to a. So the center is going to determine what this a is. So if I say at x being equal to 2, I would put a 2 right here. X minus 2, x minus 2 squared, x minus 2 cubed, and on and on. And of course, they will always give you what this is. Okay. So that's what a power series is. So now throughout chapter 6, we are going to learn what I can do with these things. So the first thing is I want to know when it converges. This is what we did previously. We had all those root tests, the ratio tests, all those tests. We are going to use those here to tell when a power series is going to converge. The difference between what I have done and what I am going to do now, this series I have now have an x, right? The ones previously, they didn't, right? It was always just a blatant, n to the third over n squared minus 4, that kind of thing. Now I have an x there. So previously, the series either converged or diverged, right? Well, now it's going to depend on what the values are for x. So depending on what my x is, it may do one thing, whereas another x may give me a whole new thing, right? So this is what this is kind of going to talk about right here, okay? So first things first, a power series centered at x being a satisfies exactly one of these. So only one of these is going to be true, but one of them will always be true. So one of these will be true. Either, the first one says, the series converges only at x being equal to a and diverges for everything else. So what this means is that it only converges if x is what the center is. And if it's not, then it doesn't work. Okay, so in this case, there's only one value x can possibly be. Number 2 says the series converges for every x. So every single value for x. So that does happen. We are actually going to see some here. Okay, But the third one is the most common one, okay? The third one says there exists a number r such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. At the values of x where the absolute value of x minus a is r, the series may converge or diverge. So that's a lot of words. Basically what it means is that there's going to be an interval on which it converges. And that's what I talk about right here. Consider a power series. The set of real numbers x where the series converges is known as the interval of convergence. So that's going to give me every value of x. That's going to make it work. If there exists a real number r such that the series converges for absolute value of x minus a is less than r and diverges if it's greater than r, then r is called the radius of convergence. If the series converges only at x being equal to a, we say the radius of convergence is r equal to 0. If the series converges for all x, which will happen, we say that the radius is equal to infinity, just because it's a big range of things. So let me show you what I mean. Example number 1, for each of the following series, find the interval and the radius of convergence. So I'm going to use every test I have learned, again, like the root test, the ratio test, divergence test, all those tests on these things, okay? So the first one, example number 1a, is the sum from n equals 0 to infinity of x to the n over n factorial. And I want to know for what values of x does this converge, okay? So first things first is I want to know which test I want to use. So then think back to all those rules we had learned, all the tests and everything. Remember we said if there's ever a weird term in there that I don't really know what to do with, I want to use the ratio test, right? Well, notice in factorial, that's weird. Algebraically, there's nothing I can really do with that. So I want to use the ratio test. So remember the ratio test, just as like a recap. The ratio test says I want to find rho, which is the limit as n goes to infinity of a n plus 1 divided by a n. I want to find that. If rho is less than 1, it converges. If rho is equal 1, it's inconclusive. And if rho is greater than 1, it diverges. Again, I use this whenever there's anything weird, right? So, got something weird, let's use that. So we're going to do the limit as n goes to infinity because I'm looking for rho. A, n plus 1, I'm going to plug in n plus 1 everywhere I see n. So this is going to be x to the n plus 1 over n plus 1 factorial. Then I'm going to divide it by what I had to start with, right? But dividing by a fraction is like saying times and then flip it, right? So n factorial over x to the n. And let's see what happens there. First things first, I have x to the n plus 1 divided by x to the n. Both of those have an x to the n, so I can cancel out x to the n, which is going to leave me on top with just x to the first, which is just x. So far on top, I just have an x. N factorial over n plus 1 factorial. We did a lot of these whenever this was taught, right? Remember, n factorial means we're going to do n times n minus 1 times n minus 2 forever and ever up until I get to 1. Then divided by, do the same thing for n plus 1, means I would start at n plus 1. Minus 1 gives me just n. Minus another 1 gives me n minus 1. Minus another 1 gives me n minus 2, on and on, till I get down to 1. So what happens here is I can cancel out the n minus 1, n minus 2, and everything else. And all I'm left with is n plus 1 in the denominator. So n plus 1. So the limit here isn't very hard because the only thing that's changing is the n. As n gets really big, the denominator gets really big, which means the entire fraction gets really small. So this limit is equal to 0, which by the ratio test means this converges. So what I have just found is it converges no matter what, right? Because I didn't even use the x right here, right? I just found that it worked. So what this means is that it doesn't matter what I plug in here for x. It doesn't matter because it's always going to converge. Even if this was 100, n is still going to be really big, right? Even if this was 1,000, the n is still really big. So it doesn't matter what value I plug in there for x, it will always work. Therefore, the interval of convergence, which again tells me what values of x will work, is negative infinity to positive, simply because any value for x is going to work. And then the radius of convergence, since it works for every x, is going to be, hang on, I can't spell and talk at the same time. There we go. Is going to be equal to infinity, again, because it works for every x. Once again, as I always say, if that doesn't make sense, reach out and let me know. Let's do another example. This is still example 1, just B. Sum from n equals 0 to infinity of n factorial x to the n. So once again, there's something weird in there, so I'm going to use the ratio test. So do the same thing as what I did. Again, because there's a weird term right there, do the ratio test. So rho is going to be equal to the limit as n goes to infinity. Remember, I start with n plus 1, so I'm going to plug in n plus 1. That's going to give me n plus 1 factorial x to the n plus 1 over, and then just the original one that I had, which was n factorial x to the n. So let's see what happens here. As we said on the last one, so just rewind and watch that, n plus 1 factorial divided by n factorial is going to leave me with just an n plus 1. This time it's on top because the larger one is on top. So n plus 1 is going to be on top. And then x to the n plus 1 divided by x to the n. Both of these have an x to the n. And I'm left with x to the first, which is just x. Now, your first thought would be, as n gets really big, right, this whole thing gets really big. And that's true, except when x is a certain thing. Let's think about that really quick. What's the only value of x that would kind of mess that up? So think about it. And the answer is, if x is equal to 0, then this whole thing would be equal to 0, right? But if it's not, if x is anything else, then this is getting really big, and the limit is equal to infinity. So what I would put is it's equal to infinity if x is not equal to 0, and it's equal to 0 if x is equal to 0. Let me know if that doesn't make sense. So what this means, this only converges in this case. That's the only time it does. And it's going to diverge anywhere else. So it only converges if x is equal to 0. So that makes the interval of convergence, it only works for one thing. So instead of it being like a range, like from here to here, it's just going to be a set with the only answer being 0. That's the only possible x that'll work, which makes the radius of convergence, since it's only 1 point, there's no length there, so the radius is equal to 0. 1 point I want to make, actually there are 2 points. But the first one, the 0 here does not come from the number I have inside of here. This could have been 50, and I would still put this for the R, again, because that's going to tell us how wide the range is. Since this is only 1 point, there's no gap. You know what I mean? There's no range. It's just 1 point, so R is going to be equal to 0. It just so happened that the interval was the same thing. But that doesn't always mean they are going to be the same thing. Just want to make that clear. Another thing I want to say is that this may not have been immediately clear, okay? So at your first glance, you probably would have just written down this, because as the n gets really big, the whole thing will get really big, right? Which would make you say it diverges, and so it doesn't matter what it is, it will always diverge, right? But think about what we said on our note sheet, okay? One of these three things is always true, right? None of them say that there are no values for x in which this will work. There's always at least one. So if you work it out and then like I get this and I say, so there's no x's, done deal. You automatically know that's wrong, because that's not even a choice. One of these three have to be true, and there's always at least one, okay? So again, how I can tell, this would converge if it was equal to 0, which happens when x is equal to 0. Once again, if that doesn't make sense, then let me know. Reach out. Okay, that's example B. Example C, going to be the sum from n equals 0 to infinity of x minus 2 to the n over n plus 1, 3 to the n. So again, let's try to pick what test I want to do here. Your first thought may be the root test, because I have a power of n here and a power of n there, but I can't actually use the root test because there's not a power for n on this term. So the root test can't be done. So again, this is kind of weird. It looks hard. Let's do the ratio test, because it looks weird and it looks hard, and I don't really know what to start with. So let's start there. Personally, the ratio test is my favorite test, because it seems to always work, and that's not true. It seems to work when I need it. You know what I mean? If there's one where I'm not sure, the ratio test will normally help me out. So that's my favorite one. That's what I'm going to use here. So rho would be the limit, n goes to infinity, plug in n plus 1, just like we have been doing, x minus 2 to the n plus 1. Plugging in an n plus 1 here would make it n plus 1 plus 1, which is n plus 2, 3 to the n plus 1. Then I'm going to divide it by the one I started with, which is like saying times and then flipping it, right? So times n plus 1, 3 to the n, over x minus 2 to the n. And let's see what happens there. So first things first, I have x minus 2 to the n plus 1 over x minus 2 to the n. Both of them have an n, so cancel out the n. Leaves me with x minus 2 to the first on top, which is just x minus 2. N plus 1 over n plus 2, not really anything I can do there, so let's hold off on that. 3 to the n over 3 to the n plus 1. Both of them have 3 to the n, so cancel that out. On the bottom, I'm left with 3 to the first, which is just 3. And then again, there's nothing I can do with n plus 1 over n plus 2, so just leave it there. So the limit of this looks pretty gross, right? It looks hard. But remember, I'm only looking at the n, right? X minus 2 over 3 doesn't have an n, so I don't really have to worry about that, right? As n gets really big, n plus 1 and n plus 2 are going to grow at the same rate, because I have an n right here and an n right there. So n plus 1 and n plus 2 are growing at the same rate, which means this limit is 1. Again, because my highest term on top is an n, highest term on the bottom here is an n. N over n cancels out, leaving me with just 1. So x minus 2 over 3 times 1 is just x minus 2 over 3. But remember, the ratio test says that I have to do the absolute value of it. So make sure you're doing the absolute value the whole way through. Boom. And that's it. That's all that I've got. In the 2 I've done before, I got like a value, right? So then I could just stop and I was good. I don't just get a value here. I get a number in terms of the x, which means it's going to take a little bit more work on my part. Remember, the whole idea is I want rho to be less than 1. So what I'm going to do, set this to be less than 1 and solve it for x. That's going to tell me what values of x this will work for. Again, the reason I haven't had to before this is because I just got a value. I got 0 here. I got 0 on example A, I'm pretty sure. Yeah. And so I didn't have to do anything else. This is in terms of the x. So I've got to do something about it. So set it less than 1 because for the ratio test, I want rho to be less than 1. So set it less than 1. Since I have an absolute value here, I know it could be -1 or positive 1. So -1 is less than absolute value. Oh, absolute value is the whole reason I split it up. Again, the absolute value means it could be -1 or positive 1. So -1 is less than x minus 2 over 3 is less than 1. And I want to solve this for x. I'm saying over 3, so to get rid of that, multiply everything by 3. Multiplying this by 3 gives you -3, less than. I still have an x minus 2 left here. Multiplying this by 3 gives you 3. Then to get the x, I just add 2. Adding 2 over here gives you -1. Adding 2 gives you 5. So when x is between -1 and 5, this is going to converge. That's what this means. Once again, if any of that doesn't make sense, then let me know. So this is all fine and good. This means I'm in case number 3, right? But remember, it says at the values where it's equal are, the series may converge or diverge. So we don't know what's happening at -1 or at the 5, right? So I have to plug those into the original and see what happens. So let's start with the -1. X equals -1. That makes the sum n equals 0 to infinity. Plug in the -1 here. -1 minus 2 is -3 over n plus 1, 3 to the n. So let's see what happens here. I have -3 to the n. It looks a lot like 3 to the n except for the minus sign. So I could actually cancel those out. I can cancel these out, leaving me with -1 to the n over n plus 1. This is an alternating series, which means we can use the alternating series test, which needs us to make sure everything is decreasing, which it is. 1 over n plus 1 would be like 1 over 2, then 1 over 3, then 1 over 4, 1 over 5. That's decreasing. And that the limit is equal to 0, which it is. So this converges. So at the -1, it works. So put less than or equal to there because it works. Now I've got to try it at 5. At x equal to 5, I get the sum from n equals 0 to infinity. 5 minus 2 is 3. So that's going to be 3 to the n over n plus 1, 3 to the n. 3 to the n's cancel out, leaving me with just 1 over n plus 1. I can use the limit comparison test with 1 over n to see that this diverges, because I can compare it to the harmonic, which is 1 over n. So when x is equal to 5, it diverges. So it does not work at the 5. So what this means is our interval of convergence, -1 is included. So we're going to go -1 up till 5. 5 does not work, so put parentheses. But the -1 will work, and so I put a bracket there. 5 does not work, so put a parentheses there. The radius is the radius of my range right here. I'm going from -1 to 5, which is a length of 6, right? Because I would go 6 spots. Half of that is equal to 3. So the radius is equal to 3. Again, because the total length of this guy right here is equal to 6, half of that is 3. Please let me know if any of that does not make sense. Example D kind of works like that one does. Sum from n equals 0 to infinity of x to the n over the square root of n. Once again, got some weirdness, so let's go ahead and use the ratio test. Rho is equal to the limit as n goes to infinity. Plug in n plus 1 gives us x to the n plus 1 over the square root of n plus 1 times, then flip it, square root of n over x to the n. Remember to do the absolute value of this. I should have been writing that on all of these, and that's my bad. X to the n plus 1 over x to the n. Both of those have an x to the n, so cancel that out. X to the first is what I have left, so that's just x. And then square root of n over the square root of n plus 1. There's nothing I can do there, so just leave it. I'm taking the limit for the n, right? So looking just at the terms with an n, my highest term on top is the square root of n. Highest term on the bottom is the square root of n. They cancel out, making this whole guy equal to 1. So all I'm left with is the absolute value of x. If that doesn't make sense, let me know. But again, since this is the ratio test, the idea is I want it to be less than 1. So set that less than 1, and let's solve this for x. Since this is the absolute value, I know it could be -1 or +1. And what's really nice about that, it's already solved. We're done. Our last one had some more stuff in there, right? This one's done. I have already solved it for x, so we are good to just stop there. Remember though, I've got to test this now at -1 and +1. So let's go ahead and do that. For x equal to -1, my series is going to be, plug in -1 there, -1 to the n over the square root of n. This again is an alternating series. So I need to use the alternating series to test. Remember, this means that it has to be decreasing. So 1 over square root of n. Plug in a 1, you get 1 over 1. Plug in a 2, you get 1 over square root of 2. Plug in a 3, 1 over square root of 3. Plug in a 4, 1 over square root of 4, which is 2. On and on, you can see that is decreasing. And then make sure that the limit is equal to 0, which it is. So I'm good. This one converges, and for the -1, it works. Now try a 1. That would make it 1 to the n, which is just 1 over square root of n. This is a p series, which remember looks like 1 over n to the p. In this case, our p is 1/2 because this is the square root of n, which is like saying n to the 1/2. P series says that if p is less than or equal to 1, it diverges. If it's greater than 1, it converges. Therefore, this diverges. So for 1, it does not work. So the interval of convergence is going to be bracket -1 to 1 parentheses. The radius, again, is half of the length. This length is 2 because I hop over 2 spots. Half of that is 1. If any of that doesn't make sense, please let me know. Moving on to example number 2. These always trick people up, but this is definitely the easiest part of what we have done. Don't let it scare you because it looks hard, okay? Use a power series to represent each of the following functions and find the interval of convergence. So, the first one, 2a, well, 2a is the function f of x equals 1 over 1 plus x cubed. So I want to try to write this as the sum of some stuff. That's what I want to do. That's where I want to get to. So let's look at this and see if it looks like a series that I know. So pause it really quick. Let's think a little bit about this. Is there a series that I know that I have learned that kind of looks like this does? The answer is this kind of looks geometric. Because remember, what those were, we learned this in chapter 5, right? This was whenever I had the sum of a r to the n. I believe back then we had n minus 1, but our sums started at 1. All of our sums here are starting at 0. Since they're starting at 0, we can leave it as just an n. And what we said is that this was equal to a over 1 minus r, as long as the absolute value of r was less than 1. Notice this is strictly less than 1. Okay? This kind of looks like this a little bit. The only thing is that I have 1 plus right here when it should be 1 minus. That's the only thing, right? But I can rewrite this. This is like saying 1 over 1 minus negative x cubed. Is that fair? Does that make sense? Because this would make it plus. Now, this looks like that does. Where our a is what's on top, which is a 1, and our r is what's right here, which is negative x cubed. So that means this is equal to the sum from n equals 0 to infinity. A is a 1, so just leave it blank because it's like saying times 1, so that's fine. R to the n. R is negative x cubed to the n. Easy enough. That makes sense? So the only thing is that I still need to find the interval of convergence. And the only thing I have to go by is, remember we said absolute value of r has to be strictly less than 1. Because we did say if the absolute value of r is greater than or equal 1, it diverges, right? So strictly less than 1. So we said our r was negative x cubed, so the absolute value of negative x cubed has to be less than 1. The absolute value means it could be negative 1 or positive 1. The minus sign right here, we hate it, so divide everything by negative 1. Remember, dividing by a negative is going to flip my sign. So it's going to be 1, flip the sign, x cubed, flip the sign, negative 1. Take the cube root of everything to get rid of the cubed. And cube root of 1 is just 1. Cube root of the negative 1 is just the negative 1. So what I get is negative 1 to 1. R, remember, it's half of my length, so that's going to be 1. Once again, on the last ones we did, we had to test these guys right here. We don't have to here because it's strictly less than. So I don't have to test these out. So interval convergence and the radius, and the series is right here. Any part of that doesn't make sense, let me know. Last example for this section is 2b, or not 2b. I'm hilarious. Okay, that's going to be the function f of x equals x squared over 4 minus x squared. So same thing here. This kind of looks like geometric, which is a over 1 minus r, and unlike our last one, this already has the minus sign. But be careful. I'm not exactly right yet, because the only constant in this guy is the 1. This has to be a 1. I don't have a 1 right here. I have a 4. So I need to divide everything by 4 to make this a 1. Okay? So this is going to become, again, divide everything by 4. So x squared over 4 for the top, over 4 minus 4, which is 1, minus x squared over 4. So now it looks how this one does. Our top is our a, which is x squared over 4. The radius is what's being subtracted, which is also x squared over 4. So the series is going to be n equals 0 to infinity. A was x squared over 4 times r was x squared over 4 to the n. Easy as that. But now we need to find where it converges. Remember, we want the absolute value of r to be less than 1. R in our case is x squared over 4. Again, the absolute value means it could be -1 or +1. Multiply that by 4. -4 is less than x squared is less than 4. Take the square root of it. Anything with the square root, and I'm realizing now the mistake that I made. So bear with me. Absolute value of x squared divided by 4. X squared is always positive. 4 is always positive. So all of this inside is always positive. So I actually could have just removed the absolute value signs. Let me show you why doing what I did was wrong. My next step would be to take the square root. Square root of -4 isn't anything that's real, so that doesn't help me. You know what I mean? So my bad, my mistake, erase that. Once again, just to clarify what I said, x squared is always positive, 4 is always positive, so x squared over 4 is always positive, so I can just ignore the absolute value signs. Now times by 4. Take the square root. Remember, the square root of 4 can be +2 or a -2. That's where I would end up with -2 less than x is less than 2. Again, because when I take the square root of 4 can be +2 or the -2. Then once again, there's no need for us to test these because r has to be